So I'll do that. Question announcement? Sure.
复旦的自动免考，这学期不要考错了挺好。
So this is a question sort of announcement. The fourth problem set is due tomorrow, and there is a question to you, the audience of this class. Would you like to have a fifth problem set? It should be of computational nature, sort of like a MATLAB/Python thing, which would go in the sense that if you would like to be graded on 5 problem sets, you could attempt it. If you don't want to, you don't have to. Does this sound like okay? Or you don't want to do this because you want to focus on the projects? Who likes the idea? Please raise your hands.
Which idea?
Which idea? The idea of having this fifth problem set. Or who does not want to have a fifth problem set? And we're split 50-50 here. You guys are not helpful. I guess we'll cook something up. Yeah, question.
I can't just make it optional and then that would be great.
It is going to be optional.
Let's just make it
We say not optional.
I think it was not optional, no.
那要有的就是刚才说第一个最好的是什么
Python program.
Okay. So let's start. Fewer people today. Not everyone survived the battle with the turkey. So today is going to be a lecture on online prediction, on online methods. And on Wednesday, we can either have another lecture on online prediction, or we can have a lecture on sample complexity of neural networks. We can vote again, if you'd like. Or maybe you want to wait until the end of the lecture to see which one you like. OK, so can computers read your mind? Yes? Okay, maybe not everyone agrees with you. So this is a game where I believe it's written by Joachim Freund and colleagues. So the idea here is to, well, you're going to be moving a red dot, and the computer is going to be moving the blue dot. The idea is to get to the end as fast as possible, and you will get to advance if the computer did not predict your move correctly. So you're going to be entering 0, 1, a bit string, and the computer will advance if it correctly predicted your move. Okay? The setup is clear. You might have seen this already. I like to show this in the beginning of the first online lecture. The idea is that if you can input a random sequence, what will happen? So the computer advances by 1 if it correctly predicts, and you advance by 1 if it did not correctly predict your input bit. Right, so if you could input a random sequence, what would happen? It would be a tie, right? So plus or minus central limit theorem, square root of I guess 100 roughly. I think there are 100 moves, maybe a bit less, 50 moves. Anyway, the point is that the person cannot enter a random sequence. And last year I asked Tommy to participate. Does anyone want to participate this time? Any volunteers? You just have to input a sequence of bits. Okay. Yeah. So we'll play anonymously unless you want to log in. And we'll make it hard. Okay. And it's just left-right. And you should go relatively fast without thinking too much.
Ready?
Yeah, you can look at the screen.
Well, I think I'll be less biased if I don't look. Oh,
You're Try to be random.
Okay, I am.
You're not trying hard. Random. really predictable. Oh, that's one of the worst scores I've seen.
Okay, I'll finish.
Just kidding. Okay, anyway, I invite you to play at home, not now. Let me close this. How do I do this? Screen out. Okay. Anyway, so the idea is that what is the computer trying to do? The computer is trying to pick up on a variety of patterns in one's play, right? And of course, if there are no patterns, if the sequence is truly random, then one shouldn't be able to do this. And I'm sure that many of you played a rock, paper, scissors, right? It's a fun game, well, to a certain extent. I mean, you really are trying to get into the mind of the other person, right? Like you're trying to figure out these little cues. Like the person seems to be switching to a rock after losing with scissors, or something like that. Or the person seems to be staying with the choice if they won, right? These are little statistics that you keep in mind, right? So imagine that you had to write this program that I just displayed. So what would you do? What kind of method would you propose? Anyone? Some ideas? Back, yeah? LSTM, yeah. Let's just take the deep neural network and throw it at. Maybe, yeah. I don't know how that would. Something even simpler, maybe. Yes. Majority vote of the last 5 moves. Maybe that's a good predictor. I don't know. You can try that. What else? Yes. Some model, like some K-Markov model where you estimate the probabilities of predicting one given the past few bits or past few outcomes and past few predictions on your side as well, right? So, in fact, this game was studied, or I don't know, was studied by Claude Shannon and David Hagelbarger, I cannot pronounce the name, in the 50s when they were in Bell Labs. And they actually built a machine. It was called a mind-reading machine. And a person could just press buttons, not like keyboard buttons, the actual buttons. And there would be a lights lighting up, if the machine correctly predicted the outcome and so forth. It was able to predict the moves of the player significantly better than 50%, right? So that's the only thing we're aiming for here, above 50%, right? We can't predict it too well, but at least better than 50%. And maybe in the stock market, that's all you need, right? Just need 51%. So what are some features of this setup? So one feature of this setup is that the data are not IID. I think everyone will agree that data is just not, like you can't represent this as a Bernoulli IID. Right? That's a really bad model, unless you're playing with a dog or something. So another feature of this problem is that data comes online, and you're making predictions, and you're incorporating the new data point, right? Somehow, as data arrives, you first try to predict it, and then you incorporate it into your corpus of data. And this is the signature of online methods. First, online streaming of the data, and second, you test yourself, and then you incorporate the data into your data set. What is interesting about this paradigm, and I will talk about this more later, is that there is no split into a test and train data. There is no problem with having a bias due to evaluating yourself on the empirical, f hat evaluated on the same data on which it was trained, right? So somehow, in the setup, first it's natural for many of the problems out there in the wild, right? You rather than getting a huge set of data and treating it as IID, what you want to do is you want to adapt online, incorporate data one point at a time, and the nice feature is that there is no split between test and train. Again, you test yourself at every time instance, and you test yourself on the same sequence on which you're training, right? You're only able to do this in the online mode, right? In the offline mode, somehow it has to be a split into a train and a test, maybe a validation set. Okay. All right. So let's try to write this problem more mathematically. We're going to have a sequence of bits, y1, y2, yn. This is the sequence we're trying to predict. This is the sequence that was entered by a human, let's say. And suppose that the sequence lives in a plus minus 1, right? So each element is plus minus 1. And I'm going to assume that n is fixed and is known to everyone. It's a finite length problem. You can relax this typically. So it's not a big deal to assume that n is known to the forecaster. Okay, so we're the forecaster. We're the algorithm that's trying to predict the sequence, and we're trying to pick up on any patterns in the sequence, right? By the way, when I said that the sequence cannot be modeled as an IID process, of course you can say, well, of course it can't be modeled as IID, but maybe it can be modeled as let's say a autoregressive process or some kind of a time series. You open a big book on time series and try to model this problem as a time series. And maybe for this problem that might work. Maybe it's enough to consider some K a Markov model. That might be true. There are other situations such as prediction on a social network, for instance, where it becomes really difficult to try to model the dependencies of this person on the neighborhood and so forth. So if you were to write down a true probabilistic model, it would be really difficult. So this is an alternative, and not necessarily a better approach, but it's an alternative approach that you can try for predicting a sequence. So our predictions will be denoted by y hat 1, y hat 2, y hat n, and they're again going to be plus minus 1 for this for the let's try this. Okay, this is good. Okay, and I'm gonna hide the dependence, but you should realize that y hat t depends on everything observed so far, right? The prediction at time t depends on everything observed so far. So that may be y1, yt minus 1, right? So of course I'm just gonna write y hat t, but it is a function of the past. It can also be a function of your own predictions. That turns out to be not so important in the results that I will state. Okay. Again, the hat is there to remind you that this is a data-dependent quantity. It is a function of the past data, but unlike the f hat that we had before, it's not a function of all the data. It's just a function of the prefix. Okay, so what is it that we would like to minimize? We would like to minimize average number of mistakes. So let's say t goes from 1 to n, and we look at the indicator that y hat t is not equal to yt. So this is an indicator of whether we got the result correctly or not. And what we would like to do is we would like to say the following. And it will seem crazy at first. We would like to say that no matter what sequence you enter, the number of mistakes, the average number of mistakes that I'm going to incur, is at most some function of the sequence. Now I haven't said much, but this is the goal that we would like to achieve. We're going to pick some function phi, and we're going to say, no matter what sequence you give me, I would like to have a number of mistakes, at most that function phi of the sequence. Okay, so here I would like to say for any y1 through yn, plus minus 1. Right? So for any vertex of the hypercube, you can think of it that way. This should hold. Now, generally, this is not. Generally, you cannot minimize this object for all sequences. The reason is the following. So imagine that you have for a second, a deterministic algorithm. So your y hats are deterministic functions of the past. And consider the sequence which is exactly opposite of what this deterministic function predicts. So on that sequence, you're going to do terribly. Right? On that sequence, you're going to have an average number of mistakes equal to 1. So there are two things that we're gonna say. So first is we're gonna say I'm gonna allow randomized algorithms where we're gonna have an expectation of this quantity over the randomization of the algorithm. Okay, not over data, but over the randomization of the algorithm. And the algorithm is instead going to be parameterized now by a bias of a coin flip, right? So all you have to do is to decide at round t, what is the bias of the coin with which I'm going to predict +1 or -1. So that bias is a number between +1 and -1, right? That's the expected value of y hat. And again, this is a function. So beta hat is a function now of at time t of y1 through yt minus 1. Right? A deterministic algorithm simply chooses beta to be equal +1 or -1. This is the bias with which the y hat t is chosen. Is it clear? Please ask questions if I'm not being clear. Yes?
So it's here that the assumption that y hat is something that the previous y hat is not trivial, right?
Sorry?
It's here that the assumption that the current y hat is not something that the previous y hat becomes a non-trivial assumption.
So y hat is, well, its distribution depends on the previous y's.
But not
Oh no, y hats, yes, that's right, that's right. Yeah, you're right. Yes?
I think regarding that question, I think in the deterministic part, it probably doesn't matter if you don't write like y hat,
Exactly.
y, but
Exactly.
here it matters.
Here, you can show that it doesn't really matter. Let's just assume that we think of functions phi, which are only functions of the sequence. Okay. There are results where it becomes important to include your own predictions, but we're not going to talk about those. Right? Let's just consider the simpler situation. Yes?
Aren't you still kind of implicitly assuming a probabilistic structure on the y?
No, because the result holds for all y's.
But for the predictor to be, well, it doesn't. So, but it seems like for the prediction to work, you need that the knowledge of the previous y's, like as a Bayesian network, like you get screening, like the previous y is positive current y. There's no additional correlation. Like.
Let me talk more about this and try to convince you that this is a much more relaxed setting somehow. Yes. Y's in this setup, Y's do not.
It's not adversarial.
It's not adversarial. However, most of the results that I will state extend to non-oblivious adversaries that see what you're doing as well. So the sequence can be adjusted. Yes?
What we are doing is the expectation over y hat t. I'm expecting overall distribution of y hat over
Yeah. So y hat t is a coin flip plus minus 1 with the mean beta hat t.
Do you also expect expectation over all possible previous sequences?
No, so this is conditional expectation. So to be more precise, I should write this really as a conditional expectation given the past.
So that expectation is due to a random algorithm.
Just the algorithm's randomization at this current time step. So let me put a t to respond to this. This is a conditional expectation given that you fix everything that happened in the past. Good. Okay, so let me try to explain what I have in mind. For me, the modeling choice is going to be shifted away from probabilistic modeling of the sequence, which is what you're referring to, and onto this function phi. So by choosing this function phi, I'm going to input my prior knowledge about which sequences I'm hoping will appear. However, this need not be a knowledge that comes from some probabilistic modeling thinking. Okay. But let me state one more result before I continue with this line of thought. So let's look at this function. Expected, just what I wrote here. So this is let me denote it by mu sub a of the vector y, and let me denote this by a vector y. So this is going to be denoted by vector y. So the vector y is a vertex of a hypercube, right? Plus minus 1 hypercube. Okay, so you fix an algorithm. This quantity, the expected number of mistakes you're going to make on average, is a well-defined function of the sequence, right? The left-hand side only depends on the sequence, and that's the meaning. The number of mistakes. Mu stands for the mistakes. Okay, mistakes. So let's look at. Let's look at the following quantity. Let's look at the average of the algorithm mistakes averaged over all possible sequences. Can anyone just guess what that number should be? I'm going to take this average number of mistakes, and we're going to try to average over all 2 to the n sequences. Sam? I divided by n, so it's just 1/2. Yeah, that's correct. So it turns out that this is equal to 1/2. Let's see if you agree. So suppose that you have a deterministic algorithm. For a second. You have a deterministic algorithm. And it makes, on a sequence y, it makes 100 mistakes. How many mistakes would it make on the sequence that's negation of that? The minus vector y. Well, n minus 100, right? And in fact, this thinking tells you already that you can match every vector y, every vertex of the hypercube with its negation and get 1/2. And now you can go through the whole hypercube and you're just going to get 1/2. And this extends to randomized algorithms as well. Yes?
So we're going to say deterministic algorithm. Shouldn't the algorithm look at the sequence?
Yes. The algorithm. So this is a deterministic algorithm that just looks at the sequence. And a randomized algorithm is a bit more general. It sets up a distribution for the y hat t with the mean beta, which looks at the sequence. But the sequence so far.
So y will make like n minus 100 mistakes on the negated.
Why it would do that?
Yeah. Like it's not making the same prediction because sort of like you have a new sequence in.
But it was so. Let me see. I think you're right. I thought I had this argument before. You're right. You're right. Let me prove this for you. You can write this as just the argument is a little bit more subtle. So let's go through this. You can write this as the expectation over epsilon. So epsilon now is going to be a vector epsilon 1, epsilon n of Rademacher random variables. Okay. So this averaging over 2 to the n sequences is the same as taking expectation over an epsilon, right? So that's equal to mu a of epsilon. So now you have two expectations. One is in the definition of mu a. Let's write it out. Expectation with respect to epsilon. Expectation with respect to the randomization of the algorithm. 1 over n sum of indicator y hat t not equal to. But now it's not yt, it's the epsilon t. Right? This is just the definition of the mu. Right? Now what I'm going to do is I'm going to swap one by one these expectations. And I can only do it one by one because the y hat t depends on the past epsilon, so I can't just swap the expectation with respect to randomization of the algorithm and the random sequence all at once. I can do it only one by one. But at every time I do this, I cannot predict a random coin flip. So I get 1/2 for this indicator. Expected, no matter what algorithm you choose, it cannot predict a random coin flip. Right? So I just have to do this coupling of this two sequences carefully, one by one. And that will give you the result.
Why does that have to be a big one?
Because I'm averaging over with a uniform distribution over the hypercube.
You are assuming that you are.
I just wrote something down, and I'm claiming that it's equal to 1/2. Why did I choose a uniform distribution? I'll explain in a second. This was my choice. Everyone is clear about this argument? Please ask. Yes?
I can see why it's a random conflict, but I'm confused why you can't predict a random conflict.
Well, you can't predict a random, right? So, so no matter what, right? I mean, whatever the prediction you choose, the outcome has probability 1/2 of being +1 or -1. So you can't do better than 1/2 in that case. You're just exactly summing over correct and incorrect. 1/2 you're going to be correct, 1/2 you're going to be incorrect. You're gonna get 1/2 for the indicator, right? No matter what the algorithm is. If you could predict randomness, I wouldn't be here. Yes. I just want it for uniform for now. Let's just do it uniform. What is the so this is the claim, right? This is our little lemma, which says that no matter what algorithm you choose, it will have a certain expected number of mistakes on every sequence, and on average that has to be 1/2. You can't beat that, right? It makes sense because we haven't provided any knowledge about what the task is, right? You shouldn't be able to do better than 1/2. Yes?
Is this some sort of no free lunch 0?
It's kind of no free lunch. Yes, exactly. It's a kind of a no free lunch theorem. But now I'm going to turn the tables, and I'm going to claim that we can use this no free lunch to our advantage. So how do we do that? Well, if I had some knowledge about which y's I care about, which sequences y I cared about, then perhaps I could make sure that this number of mistakes is small for that sequence. And I will have to pay for that on some other sequences. But that's okay because I don't care about that. Is that clear? The logic is clear? And again, note that I'm not modeling the sequences. I'm not modeling the distribution of the sequences. I'm going to have a result that holds for all sequences. It's just it's better for some sequences and worse for some other sequences. Right? I'm not going to be able to predict all sequences better than 50%. I will focus on some part of the space of sequences and care about that subset. And then I'll have to pay dearly on the other sequences. Is that clear? The philosophy? All right. So if I could think of what type of sequences would a person generate, well, probably there's going to be some patterns, right? If I'm thinking of predicting some financial instruments, maybe there will be some seasonality, right? So I can try to input my knowledge, and I will give you a few kind of tools to do that, to construct, kind of insert our knowledge about what sequences might appear. Okay. But the problem is still here, is still there. Even if I do decide which sequences I care about, it's not clear that I can make this small. It's not clear that there will be an algorithm that will achieve this when I choose a certain profile mu. Right? So think of mu as now as a profile on the hypercube. So mu, so an algorithm A induces as a function on the hypercube, right? Induces a function, let me not put a function from plus minus 1 to the n to a minus 1, not minus 1, to 0 and 1, right? That's the average number of mistakes, the indicator. But it's not clear that if I choose a function like that on a hypercube, that there will be an algorithm that corresponds to that function, right? Is it clear what my problem is? I want to model my problem by tilting this function towards the sequences I care about on the hypercube. So think of it here's a hypercube in n dimensions. I care about maybe these sequences, and I would like to make few mistakes on those sequences. I'm going to try to tilt my mistake function towards those, make it smaller, and pay on some other sequences. Yes?
Dynamic programming thing, like let's say you're at the very end.
That's right. That's exactly what we're going to do. Well, we're not going to do it, but I'm just going to state the result. So let me just consider a function phi plus minus 1 to the n to 0, 1. And I'm going to say that phi is achievable if there exists an algorithm that has that profile. Okay? If there exists an algorithm such that a mu sub a for that algorithm is, well, let's say at most phi per vertex, right? So it's dominated by phi. And let me, for the next 15 minutes, consider only phi which is stable. Suppose that phi is stable, or Lipschitz, if phi applied to anything with a +1 minus phi applied to anything with a -1, where I'm switching the same coordinate, right? I'm just looking at the value of phi here and the value of phi here on the hypercube, is no more than 1 over m. Okay, so it's a function that doesn't change too fast. It can change from one vertex of the hypercube to another vertex. It could traverse a distance of 1, right? But it doesn't do so too quickly. Here's lemma. That's roughly due to Tom Cover in 65, which says that and this is my own rephrasing of that result, which is not even stated as a lemma in that paper, but regardless, let phi be stable, or Lipschitz, then phi is achievable if and only if, well, what is one direction? So we know that we know that if you have an algorithm and you look at mu sub a, the number of mistakes per sequence at that profile, you know that in expectation over all sequences, it has to be 1/2. This lemma says that this is also a necessary, also a sufficient condition. So expectation over epsilon of phi of epsilon is, let's say, at least 1/2. Okay. And if you make this equality, then it's achievable with mu equals to phi. So this inequality and that inequality go hand in hand. So this is a very peculiar very interesting result. It says that whenever you choose a phi function, which is Lipschitz in this sense, and you make sure that its average over the hypercube is at least 1/2, there is an algorithm that has that function as its mistake bound, or as an upper bound on its mistake bound. So again, one direction is trivial, which is what we showed, is that if you take an algorithm and you look at the mu sub a, then it has to be at least 1/2 on average over the hypercube. This says that it's also sufficient. Right? Again, the picture, if you wish, is that you have a hypercube, and you choose some phi. I don't know how to draw a function on the hypercube. You know, you have some function on the hypercube. It just assigns numbers to vertices, right? If you can make sure that the function doesn't change too fast along the edges of the hypercube, and its average over the hypercube is 1/2, then there is an algorithm that achieves it. Okay? So this gives me a passport, if you wish, to start modeling my problems using this idea. Because now I can choose a function that corresponds to my knowledge about the world. And there will be an algorithm that will achieve it. Moreover, the algorithm is closed form, and I can just write it down. I will do that maybe a bit later. Okay, so let me give you an example. So suppose that you take phi of the sequence y to be min between a, how should I write this? 1 over n sum of y t. Oh no, I need to shift it. Okay, let me write it like this. Y bar and 1 minus y bar, where y bar is proportion of ones. Okay, you can write down in mathematics what that is. So y bar, not to be confused with the y vector, y bar is a proportion of ones in the sequence. And 1 minus y bar is the proportion of minus ones in the sequence. So what I'm saying is, I think the user will enter an imbalanced sequence. Right? So what will phi catch? Phi will catch any imbalanced sequence. Suppose that the sequence is 30-70, imbalanced. 30% ones, 70% minus ones. Then this function phi will be 30% because it's the minimum of the two proportions. Right? Now, is this function achievable? Because this would be the first thing I can try if I were to implement this algorithm that I showed you, the game, right? Because the person cannot enter a balanced sequence, right? I mean, of course they can, but they need to know that the algorithm is trying to catch that, right? Of course I can enter 0, 1, 0, 1, 0, 1, or minus 1, minus 1. So is this sequence is this function achievable? It's not. Why? Because the expected phi of a sequence, so on average over the hypercube, this function is equal to expected, you guys see here, expected minimum over y bar and 1 minus y bar. And expected minimum is, remember the homework, expected minimum is what? Larger or smaller than minimum of the expectations? Expected minimum is smaller than minimum of the expectations. But minimum of the expectation of y bar is 1/2, right? The expected proportion of ones is 1/2, and the expected proportion of minus ones is 1/2, right? Or I should put epsilon here, sorry. Let me put epsilon bar. So epsilon bar is the proportion of plus ones in the random sequence. So you see that this is less than 1/2. That's too bad, because I really wanted something larger than 1/2. Yes?
Why isn't it equal to 1/2? Why can't
Because the expected minimum is, by Jensen inequality, smaller than the minimum of the expectations.
you wrote less than, so it's actually less than, not just less than or equal to?
Oh. But this is also true.
Yeah, sure.
Yes, it's less than. But how much smaller is it? How much smaller is it? Yes? By what? At most a factor of 2 from what?
All I'm saying is if you add a factor of 2 there, so
If I add a factor of 2,
so that b equals 2 times minimum of y.
if I do 2 times minimum, okay, maybe there is a way to massage it. Let me just say, it's a central limit theorem, right? I'm asking how far the average of plus ones is from 1/2. Well, it's roughly 1/square root of n away, right? And I'm taking the minimum of that and 1 minus that. So I always get a number less than 1/2 by 1/square root of n. So in fact, even though this is true, if I were to take a phi, if I were instead to take a phi of y, which is the minimum of y bar and 1 minus y bar, plus some constant over square root of n for a small constant c that you can calculate, then indeed you will have expected phi of epsilon greater than 1/2. Okay? And now this tells me that I can catch any person entering an imbalanced sequence up to 1/square root of n type of, or a constant over square root of n type of behavior. This is a really interesting result. It says that there is a method, and I haven't told you what it is. There is a method that no matter how the sequence appears to that method, right? No matter how it's reshuffled, how it's presented. At the end of the day, if it was imbalanced 20/80, the method only roughly made 20% mistakes. The method actually doesn't need to know that number, doesn't need to know the imbalance, because it's automatically adaptive to this a posteriori proportion. If it happens to be 10 and 90, the method only made 10% error. If it was 49/51, the method would only make 49% mistakes plus this 1/square root of n. So for large sequences, you would be hard pressed to beat that algorithm on the computer, because you would at least have to enter a balanced sequence. Now, I did not use any probabilistic knowledge. I did not model anything with probabilities, right? Even though this check, this sufficient condition, sufficient and necessary condition, is has this probabilistic flavor, I did not model the sequences as probabilistic. Right? I'm saying the result will hold for any sequence. It's just the result is going to be better for some sequences and worse for some other sequences. Questions? Yes?
I think this result is kind of obvious in some way, because so if you only have 10% minus, then all you can do, an easy algorithm is you can predict everything to be plus, and then you make like 10%
Yes.
mistake. So I'm wondering.
If you knew that ahead of time, but the problem is that you don't know this. You're predicting as you go, and only at the end of the day you will know what the imbalance was. Indeed, if at the end of the day you knew that there was going to be a majority of ones, then all ones will be the right method. But you don't know this until the end.
Okay, so basically I think this algorithm is basically saying that you can do as good as you like. You can do in the online streaming algorithm as good as like as if like you know the whole like sequence.
Well, if you knew the whole sequence, you would just predict that sequence,
Yeah.
right? So you know, but this is the most basic version, and it says that you can do as well as the best constant action, which is a 1, predict 1 always, or predict -1 always, because that gives you those two results. Of course, this is the most basic version you can imagine. Does that make sense? Yes.
I just have a very basic question.
Yes.
Could you repeat what the phi function is? Is that upper bound?
Yeah. So the phi function is our modeling choice. For a practitioner says, I think I will observe this type of sequences. For instance, let's say it's a social network where nodes are predicting, people at the nodes of the network are predicting whether they like this advertisement, let's say, right? Then you would expect that there's some homogeneity over the neighborhood with the friends, right? So the person is more likely to predict what the other people predicted, right? Or what the other people like, right? So you would enter that as a knowledge about the sequence. The sequence is more likely, you're more likely to see that. Except we're not modeling it as a stochastic process, we're modeling it as just this function phi. So once you've chosen the function phi, that will define the algorithm. I didn't write it down yet, but the algorithm is just in terms of the function phi. As long as you can ensure that the function phi is achievable, you've got the algorithm. Right? Any other questions? Okay. So let me expand. I will come back to this setup in 10 minutes, but let me expand the protocol and suppose that the protocol is as follows. For t from 1 to n, so before we would just make a prediction y hat t, observe yt. Now, it's not interesting to predict sequences in vacuum. It's interesting to predict them when you have some side information, right? So this setup is you observe some xt that lives in some, let's say, d-dimensional space. These are the covariates. Now you predict y hat t. Again, let's say plus minus 1. And then you observe yt. Right? Again, it's a streaming model where data arrives one by one. At every step, you're evaluating yourself. Am I able to predict the next bit correctly or not? Once you do that, you observe the outcome, you incorporate the data point into your data set. And on purpose, I didn't write where these variables live because you can consider different setups, binary classification, regression, and so forth. Yes? Good, yes. So let me write it out, very good. Y hat t is a function of y1 through, I'm going to write it like this, t minus 1, and x1 through t. Because before making the prediction, you observe the xt. Right? That's important. So this is a bit longer than this one. Okay. And now you can write down the analog of this. Well, what do we care about? Again, it's the average. There is some loss function of y hat t yt. It was an indicator before. You can take a different loss function. And you want this to be, let's say, an expectation. At most, some function phi of x1, y1, x2, y2, xn, yn. Okay, so this is very abstract. So let me give you a particular function phi that makes sense. So suppose that I'm hopeful that some f in a class of functions, just as before we had a class of functions f, explains well the relationship yt from xt. Right? In the following sense, in the sense that 1 over n sum or minimum over f in f, 1 over n loss of f of xt yt is small. Okay? This is what it means, right? If yt can be explained from xt by some function f, in other words, some function in f captures the relationship between yt and xt, that is the loss of predicting f of xt when the true label is yt is small, right? Then this quantity is small. Yes?
So this xt I think is an instrument variable for y?
It's an arbitrary sequence. We make no assumption about anything here. So in fact, let me write it down. I want this to hold for all x1, y1, xn, y1. For any sequence of 2n variables, x, y, I want this result to hold. Yes?
So is this like this whole learning problem for another learning problem?
What do you mean?
I mean, we should find the f that somehow helps us to predict yt by xt, and then.
Yeah. So at this point, I'm just saying, I'm mathematizing this statement. Let's say I'm hopeful that I pick a class f, and one of the functions explains well y from x. This is what it means in my language. Let me write down the function phi. Okay? So what is the function phi? So the function phi that I have in mind is, let me not write the arguments. Phi is min f in f 1 over n sum of loss of f of xt yt plus I have to add, just as before, the expected minimum is less than 1/2. For very similar reasons, I have to add something. So let me call it c sub n and f. It's some constant that depends on n and somehow on the complexity of f. Okay? If I take that function, it's tilting phi towards the sequences xy, where y is well explained by some function in my class f. Yes?
So the function that predicts yt only depends on xt, or can it also depend on the history of x1 to t minus 1, y1 to t?
You mean f?
Yeah.
Good, very good. So here it is a fixed f that just depends on xt only. Yes? Good, good. You can extend it to functions that depend on some partial history. Some of that has been done. I'm just stating the simplest version. Okay? In fact, if you've seen the literature on regret minimization, this is exactly the same statement as regret against the class of functions f is c and f, which is some constant that goes down with n, right? Because I'm saying that for all sequences, my expected loss is going to be at most the comparator plus some regret, what's called the regret bound. So this is called the regret bound, because we're saying, well, how much do you regret not knowing the f ahead of time, which is the, let's say, a constant +1 or a constant -1. Here it's more interesting because it's actually a mapping from x to y. How much do you regret not knowing f ahead of time? Can you do as well as if you knew the best map from x's to y's, right? Okay? Now, it should be, well, maybe not clear, but you would think that this is a more demanding setup than the IID setup, right? So if phi is achievable, does that imply anything about the offline problem, the IID problem? Well, let's see. Suppose that you had an algorithm that achieved this function phi. Suppose you've achieved that regret bound. But now now suppose the x's and the y's were actually IID from some distribution p. Well, I'm going to assume convexity of the loss function. And then I'm going to show you that this result implies what we've started the semester with, right? The estimation error for the empirical risk minimization. Whatever this algorithm will do, I don't know, but it implies the same estimation bound as you would get from the part 1 of this course, right? That's given that C and F scales in the same way as the complexities that we've studied so far. Okay, so let's try this. So what we have is that for any x1, y1, xn, yn, bunch of commas here, what we have is that let me just choose a deterministic algorithm, right? If the loss function is convex, it turns out that it's enough to restrict yourself to deterministic algorithms. It was not the case for indicator loss, which was not convex. But now let me assume that the loss is convex in the first coordinate. Now, so what we have is that for any sequence, 1 over n sum of L of y hat t yt is at most minimum over f and f 1 over n sum L of f of xt yt plus something that's hopefully is small. Right? So this is called the regret bound. It's a particular family of phi functions. But now data are IID. Now this result holds for any sequence. So I can take an expectation on both sides. Right? Now I'm thinking of the sequence as being drawn IID from the distribution. I'm just going to take an expectation on both sides. So what I get is, well, can I edit in place? Expectation. And now it's not for any sequence, but for on average over the sequences. And now you have here expectation over the data plus Cn. Right? So this both expectations are over the randomness of the sequence. Because it holds pathwise, it also holds on average over the sequences. Now, I can think of this y hat t. Let me think of y hat t as a function of xt. Right? Of course, it's a function of everything before. I'm going to put it in the hat. And I'm going to make this explicit. It's a function now that depends on xt. Right? If you gave me a different xt, I would produce a different result. Right? So I'm just going to think of this as a function. And I'm going to create what's called a Pollack average. Pollack average, if you've studied optimization, it's exactly the same thing. Y bar as a function, it's an average of y hat t of these functions, right? Just the average function that you've produced over the path, right? It might start reminding you of the first lecture on perceptrons, where we chose one at random. Remember, we chose one W hat at random. Here we're actually averaging them, but the idea is the same. So then, with this Pollack averaging, by Jensen inequality, because the loss function is convex, we get expected loss of the okay, sorry, you need a few more steps. Okay, you need a few more steps. So that's the simplest way to do it. Let me do the left side later. The right side, if we push the expectation inside, we get a larger quantity because of concavity of the minimum, right? So now expectation goes here, and all of these terms are the same because f is fixed and xt, yt are IID. So what we get is an upper bound of expected L of f. Minimum over f and f, expected L of f. Right? Which we denoted before plus C and F. And this we denoted before by L of F sub F. Right? That was the notation we had before. Okay, now I'm going to claim that if I use this as my algorithm, then it has the correct upper bound of the minimum best in class plus something that's small. So let me show you that argument quickly. 1 over n sum of L of y hat t yt. So I'm going to use a linearity of expectation to swap the expectations. So let me do that in place. 1 over n sum expected loss. Expected. Now, let's be careful. This expectation has to be over the whole data set, or in fact, it has to be over the data set up to time t, because this y hat t Someone's playing. Okay. That was the beginning of Philip Izola's lecture. Now, this y hat t depends on y1, x1 up to yt minus 1 and xt, right? So let's write this out more precisely. 1 over n sum of expected loss y hat t. So it depends on x1 through t minus 1, as we said. Let's make it like that, right? That was our notation. y1 through t minus 1. And it's evaluated at xt, right? If we think of this as a function that was obtained by looking at these data, and now it's evaluated at this current xt. Now we compare it to yt. Okay, so now the point is that we can, well, xt, yt is just a random variable. I can just erase t, right? Right? This is the expected loss of this function, just as before. This is the expected loss of this function. Expected out of sample loss of y hat t. Except now it still depends on the past. Right? But now we're doing the average. And if we use Jensen inequality, it's going to be lower bounded by expected L of the Pollack average. Yes, correct direction. Yes.
Why y hat also depends on y?
Up to t minus 1.
We assume that y hat is just a function of x.
Both x's and the y's. Yeah, you have to, you look at the covariates, you see the outcome, you look at, right? You see the covariates, you make a prediction, you look at the outcome, and you continue like that. So what we've got is the expected, the result that we've got is expected L of y bar, not ERM, but y bar, is at most the expected loss of the best function in the class f plus c and f. Yes? Y hat t is a function of, yes, it is up to t, but I'm putting t here because I'm thinking now of this as a function evaluated at xt. I'm just splitting one xt and writing it explicitly. So this should remind you of a bound we've got for empirical risk minimization. Yes? So what was CNF? Second? Generalization gap, right? When we analyze the generalization gap, this is the generalization gap. Yes, exactly. Which is further upper bounded and lower bounded by Rademacher averages. So Rademacher averages is what we would expect from the CNF if we're in the world of IID data. But now we did a detour, right? The goal is for this problem was IID data, but we went through online and came back to IID. The question is, is this detour, does it cost you something? And kind of the amazing thing about this literature is that we know exactly when this costs you and when it doesn't cost you. And let me just say a few things. So if the loss function is the indicator, it will cost you. This detour will cost you. If your loss function is absolute loss, or if it's a regression problem where the y variable is a real value rather than a binary, it will not cost you, typically. So there's a strong connection between these two setups, IID and the online. Okay. Yes?
But if you can do this, can you do something similar, but like to relax the IID assumption
Yes.
on the original data?
Yes. So we made this huge step. We did something for all sequences, and then we said, oh, by the way, will it hold for IID sequences? Yes, it does, of course. But you could say that, okay, actually, x's and y's come from some model. Let me now see what that gives us. So this is kind of the biggest step you could have made from all sequences to IID sequences. Intermediate are some processes you could assume. So the point of this last 15 minutes is to show you that if under the right setup, if you did something for all sequences, you also get the result for IID sequences. So even if you didn't get the details, this is something to remember, that online setup gives you a result for all sequences, and as a consequence, you can get a result for the IID sequences. And sometimes you're not even going to lose anything, because this is going to be precisely matching what you had before. Now this involves quite a bit of work to show that this CNF is of the same order as what you would get from generalization gap, but that's kind of that's the basic idea. Now, this setup seems to be more appealing in situations where dependencies in the data are very complicated, and you can't model them faithfully with a probabilistic model. You see, if you assume a certain probabilistic model and then you study that probabilistic model, the result is going to be automatically false if the model is not correctly specified. And there's a study of robustness, but generally it's not clear if your model is not correctly specified, if the truth deviates from the model that you've written down. It's not clear whether the result will be at all meaningful, whether you're going to get anything out of it. Now, this is, of course, a more stringent setup where you're modeling not the evolution of the data, but what you think will work well at the end. What you're modeling the solutions, you're modeling the sequences that you think you will see in practice, right? The sequences that you care about, right? Let's say, let me give you an example. So here's one example. So suppose you're in a betting business and you're betting on teams that play, let's say, hockey. So if you're a statistician, you would say, okay, I'm going to consider the following model, that every team has some goodness level, let's call it mu, not this mu. So that mu, if the mu for this team is larger than the mu for this team, then this team is more likely to win than this team, and that's going to be the probability model. So with probability, 1 minus mu or something like that, or according to the difference in the level of the mu, you would more likely to see this win than that win, right? And you can write down different probabilistic models. Now, then you observe all data, or some large chunk of data, and now you try to estimate the mu. That's what a statistician would do. You estimate the mu, and then you try to predict based on your estimate of the mu. Now, if your model is incorrect, this could be completely a meaningless result. How would a person doing this type of analysis model the problem? Well, they would say, all right, so I'm going to have a set of functions f. I erased it. So I'm going to write down the 1 over n sum of L of f of xt, yt plus something. Okay. Now this xt will encapsulate a bunch of things that I know about the problem. Whether the game is at the in a home or away, whether which two teams play, right? So that's all encapsulated in this function, in this covariate xt. Now I'm gonna, given this covariate, I'm gonna write a bunch of functions which would predict who wins, given what I know. Right? It's relatively easy to write something of that form, right? And I'm going to collect all these possibilities together. So maybe this function will say, okay, if the mu for this team and for this team has a gap like that, then it's this one. I'm going to predict this one, right? And if it's like that, then I'm going to predict this one, unless it's a home game. Okay. So you can write down a bunch of different solutions. Note that we're modeling solutions to the problem. We're modeling what would we predict given what we know, given the site information xt. What kind of solutions are we hoping to kind of model? We're modeling solutions, not the process itself. Right? We're not modeling probabilistically the x's and the y. We're modeling what works well. Now write down this f of what you hope works well. That puts a tilt on the space of sequences, which sequences you hope to observe. You're hoping to observe sequences for which one of these f's will give good predictions of y from the site information, right? This is a different approach. This is a very quick overview of the field. The key things to remember is that data arrive one by one. There is no separation between training and test. You get tested every time you make a prediction. You keep track of your performance at every time step, and then you incorporate the data. Under certain assumptions, if you've got a result for all sequences, then it also implies the result for IID sequences. But all sequences results is stronger. You're modeling not the probability distribution generating the data, but the solutions, what you hope predicts well. And you're hoping to do just as well as that best thing, right? If you're able to say that your average number of mistakes is going to be upper bounded by this quantity, then you really, if the world behaves in a way such that one of these functions is doing well, then you're also doing quite well. Right? So it's a different setup. I only had an hour and 20 minutes to explain. There is much more. If you want, I can do another lecture on it, or I can continue to sample complexity of neural networks on Wednesday. What do you guys want? More online, or sample complexity of neural networks? Online.
Sample complexity.
Sample complexity of neural networks. Oh, it's just a bit more sample complexity. Okay, I'll do sample complexity of neural networks.